Good morning, everyone. Thank you for joining us for today's webinar, Aegis, the Next Generation in Underground Blasting Software. Before we begin, to ensure that all registrants are able to view and hear the presentation, please use the raise hand button on the left side of the screen to verify that you can all hear me. Okay, that's great. If you happen to experience any technical issues during the presentation, please use this raise hand button and we'll attempt to assist you. We will allocate time after the presentation for a question and answer session, so if you have any questions throughout the presentation, please enter them into this chat box and we'll do our best to address these. Now to introduce our presenters. First up we have Ian Lipchak. Ian is the Solutions Manager for Underground Mine Planning at CAE Mining, and he is based in Vancouver. Ian has over 10 years of mining experience in both operations and consulting. Our next presenter will be Troy Williams. Troy is a Senior Software Developer with Stroma, and he is based in North Bay, Ontario, also in Canada. Troy has spent 14 years developing software for the mining industry, with a particular focus on underground drilling and blasting. He is also a licensed professional mining engineer. Okay, take it away, Ian.
Thanks, Eloise. Good morning, everybody. So today we're going to show you Aegis, which is a brand new underground drill and blast package. And we're quite excited about it. So I'm just going to take you through a few slides first. Okay, so Aegis Advanced Underground Drill and Blast. Basically, Aegis is the next generation of underground drill and blast tool. Traditional underground drill and blast tools generally involve an application that is built on top of a CAD package or some other mine design CAD software, and then it helps you lay out rings. And it does that by allowing you to slice sections, which will be your ring sections. Once you slice the sections, then you can manually lay out each hole on each of the rings one at a time. Sometimes there's some tools to help you lay out a few holes at once on a single ring. Well, Aegis is completely different from that. Firstly, Aegis is completely standalone. It doesn't require any CAD software at all. It can create its own reports and drawings on its own. It doesn't even need to integrate with anything. You just import your data from Studio 5D Planner or DataMine Studio, and then you can go away and do your ring designs. The other thing that's different about Aegis is that it does everything automatically. So it has a high level of automation. You basically set your burden and spacing, as you will see in the demo, and it will create all the rings and charge the holes for you automatically. But then you can manually edit things from a ring down to an individual hole or an individual charge. So there's quite a high degree of flexibility as well. So the bottom line is it's going to completely change the way you design your underground blasts. So there's two modules for Aegis. There's Aegis Designer. Aegis Designer was released in October of 2013. So it's been around for about 6 months. And then Aegis Analyzer, which is going to be released in a couple of weeks in April. Aegis Designer has this completely novel interactive automated approach to underground drill and blast that you're going to see firsthand in our demo. It's very fast and efficient, so potentially it requires fewer seats than a traditional drill and blast software because the people using it aren't going to be spending as much time doing a single drilling layout. As I said before, it's standalone, so there's no CAD system required. It produces paper layouts and the ERD's output. You can quickly and easily compare multiple alternative drilling and blasting scenarios. Has a user-friendly workflow, interface, and data management. It's very visual and intuitive. And it allows the mine planners to spend more time on engineering, design, and optimization, and less time laying out drill holes and blasts one ring at a time. Analyzer is an exciting new product. It The main thing that it will do is a prediction of cavity break based on ring loading, explosives distribution, and timing. You can choose between Klein, Holmberg, and Lukacs-Banis models, and then calibrate it to a CMS survey. Then you can compare multiple blasting scenarios to see what kind of cavity break you might achieve in your blast. And so this might help you to get a better handle on things like oversize or overblasting and underblasting. Really, it's a tool that's sort of been in the domain of the blasting experts until now, but now you can use it at your mine site quite easily. In the future, they're going to be looking at adding a simulation of fragmentation, and this is currently under research. And just on that research, Aegis is developed in collaboration with blasting experts, universities, and mining operations. So it's a very research-oriented development team. And I think you'll probably get that idea when you talk to Troy. And so without further delay, I'd like to pass this over to Troy Williams at Stroma, and he's going to give us a demo.
All right, thank you, Ian. So I'll share my desktop. All right, I've got the main interface of Aegis up, so I'll start a new project. One of the things that we do in Aegis is that all of our units are strictly in metric. Everything under the hood is calculated in meters, kilograms, and seconds. To display imperial units, we just convert them on the fly. So on our main project screen, we can define some metadata about this project. So the first thing after that is to import some wireframes. All right, so we've got our wireframes loaded up, and I'm just going to rotate them into position so we can identify them a little easier. The red wireframe represents our ore shell that we're interested. The yellow represents our drifts where we're going to be drilling from. I'll just set some transparency so we can see inside them, and I'll change the color. All right, so in order for Aegis to be able to utilize these wireframes, we have to identify what they are. So I'm going to identify the voids, and then I'm going to identify where the ore is. So now that we've identified these structures, we also need to tell Aegis where we're going to be drilling from. Basically, we need to tell it which stope we're going to be designing. Since this is a long hole stoping scenario for downholes, the block is fairly massive, so we're going to have a number of stopes side by side. I'm just going to do one today for this demonstration, and it's going to be within this drift. So we need to establish a reference line so that Aegis knows which section of the void wireframes that we're going to be drilling from. We can draw a reference line in. We can import a reference line from other packages. I'm just going to put a reference line from here, from this contact to this contact. So now you see that it's placed in 3D. The next step that we need is to define our stope limits for this particular block, because otherwise Aegis will assume that it can drill holes all the way through to the contacts, which isn't what we want. Now the stope outlines, they can be brought in. The stope limits can be imported, but we have a small little extrusion tool that helps us with simple stope shapes. So I'm just going to place this around my block. And I can actually slide through my ore body based on where my reference line is, just to see how the stope limit looks. Now, one of the key criteria with the stope limit is it has to encompass the drift that we're working in. The algorithms that Aegis uses needs to determine inside and outside, and has a hard time if the drill is outside of the stope limit. Now I can turn off our ore contacts just so that things are a little easier to see. So this is the block that we're interested in. So I'm done defining what these wireframes are. The next step is to set up the different views. So Aegis is a completely dockable interface. All of these windows can be undocked and moved to multiple monitors. So we also have some quick configuration views. So we have our 3D view. We have a ring section, a plan view, and a long section. We have a number of buttons that will allow you to do quick configurations. We also have options to store custom configurations. So if you're on a multi-monitor setup and you want the 3D view on one monitor, the other views on another monitor, you can have that set up and recalled later. So the next step is to identify what type of ore we're dealing with. We have an extensive database of rock properties that you can also update and add to. So I picked granite and basalt. We don't differentiate with the block model quite yet. We are working on being able to use the block model properties to identify where all of the specifics are. So now that we've defined our ore types, the next step is to actually lay out our rings. So this is the first of our automation. This is the completely automated side where we specify a few values and our rings will be generated for us. So the first step is to tell it what drill. We're just going to use the L6C for the downholes. We have a database in behind that's completely customizable. So now that I've picked the drill, it's remembered what I've used in previous runs, so it's used those as an initial default, and you see it's already generated the rings for us. So if I scroll down a little bit in the plan view, we can see how the holes are laid out in a staggered pattern. So we've got parallel holes with a staggered pattern. So we can I can show you what happens if we don't have a stope limit defined. If I can turn this off, you'll see that it goes through, and it assumes that it can drill the entire ore body. So that's one of the reasons in this particular block we need a stope outline. And we can also select different reference line to tell it which holes we're in. Now, as far as the drill direction is concerned, this line here represents the drill direction for Aegis, and it guides the parallel holes within the rings. So if we had, for example, been drilling down to this bottom sill to the right, we would want the drill direction pointing to it, so our majority of our parallel holes would go that way. But we have some defaults for up holes and down holes. If I flipped it to up holes, it wouldn't do a very good job because there's not enough room for it. We can drill to a target line, and we can set some custom angles. All of these are more advanced options for more difficult mining geometries to address with. So now what we need to do is I need to set up the pattern burden. So this particular pattern is going to use a 3-meter burden. We're going to use a 3-meter toe spacing, and we're going to put 100-millimeter holes in. So you see every time I've made a change, it's gone through and recalculated the pattern very, very quickly. Now if I take a look at some of these rings, we'll notice that it's got a pretty good toe spacing. The burden is set to where I need it to be. So we can control different aspects of the automatic pattern generation. So if my reference line was too long, for example, we had a ring on the end that we didn't want, I could offset from the end, so it would only go up to 3 meters within it. So you can see it's offset from 3 meters. So you can use any length of reference line, and then you can customize where you want your rings placed. We can control the dump angles, so I can have it set to 75-degree dump forward. So you can see all of this is regenerated automatically. So you can see the rings are generated with a dump to them, a dump or a lean if that's your convention. So I'm just going to set them vertical for now because that works best for this. We can control whether the holes are staggered or not. We can flip the look direction. So in this case, the look direction is defined by these little arrows, so it's pointing towards the end of the drift. We can limit the number of rings that we generate, so if you only need a few rings. We can control the sweep angles. That's how high up the ore goes. That's how high up the rings, the holes will be generated based on this pattern. So if I set this to -135, you'll see on the left-hand side that it's actually generating holes up a little bit higher. Okay, I'm going to increase the minimum collar spacing for these holes to about 0.25 meters, just to give them a bit more space up in the collars. So you can see there's at a minimum of 0.25. So we can control minimum hole length. If in this case it's set to 1.5 meters, so it will not draw any holes that are less than that. We can set a maximum hole length. By default, it takes whatever is set on our drill. We have a maximum hole length for the drill, so if I attempt to set it higher, it won't allow me. But I can certainly set it shorter. So now what it's done is it's made sure that the maximum length of our holes is 25 meters. So in this case, if I needed an uphole pattern in this bottom cell, we could take care of that as well. We could put it in, or we could define separate stope limits to take care of that as well. So if we take a look at some of these rings over here, we can adjust how the holes interact with the ore contact. So if I needed to extend the holes past the ore contact by, say, 1 meter, I could set it to 1 meter, and all of these holes would be linearly extended 1 meter past the contact. If I needed to shorten them, for example, if there's I know at mine up here there's arsenic associated with the contact, and they don't want to get that into the process, so they stop short of the contact. Okay, and we can actually ignore the contacts as well, so that it'll just drill the holes straight through. The only problem with this option is that it applies to all of the rings. It doesn't just apply to one. We have options later on in the program in the semi-automatic mode where we can do that. So in this case, this particular ring is just drilled straight through into host rock. Now we can also extend holes to breakthrough. For example, we may want these two holes to extend to the breakthrough, so we can set that up. But again, the only problem with that is it applies to all the rings en masse. So we may end up with situations like this, which may or may not be completely valid. But we can always go through and edit these rings later and delete the holes, move them around by hand if we need to. The whole idea with the automatic portion is to get as close to 100% as you can. If you can get 80% of your design done, that's great, because we have semi-automatic modes that will help out to do the rest. So I'm going to pick my explosive. We have an explosive database. We can control whether it's coupled or decoupled by simply changing the diameter of the explosive charge. We can control its plug distance, so that detects any breakthrough holes. So that detects any breakthrough holes. So these 3 holes are breakthrough, and it will set a distance from the bottom of the hole to the bottom of the charge. We can control our loading delta. That is how the holes are staggered. So I can set it to 1.75, and what it's doing is it's creating a sphere around the charge of 1.75 meters in diameter, and it's sliding that up the charge until it encounters 2 adjacent charges, and that's where it decides to stop the charge at. So we can add decks. So it goes through and decks all of the charges. We don't need that in this case, so I'll just return them. We've got Trojan Spartan. We just add a primer and a detonator. So now we've got quite a few primers in the charges themselves. What I'm going to do is I'm just going to increase the primer spacing to, say, 20 meters between primers. So what it'll do is it'll place the first primer, and then after that, every 20 meters after that, it'll add an extra one. So we can control where the primers are placed automatically using these offsets. So we can prime from the toe of the hole. We can prime from the hole collar. We can prime from the charge center, and we can distribute the primers equally. So I'm going to prime from the toe of the hole. One last thing, I'm just going to set the minimum collar to 1.75 meters, just so that the charge collars aren't so close. So at this point, we're pretty much done with the design and the automatic portion of it. The next step is to go through and verify that the holes are indeed in the spot you want them, and the rings are in the correct spot. So I'm going to go through that. And you notice in the plan view, my selected ring has, it's highlighted, and it has these red circles. These are what we call glyphs that we can use to control the ring. So I'm just going to rotate the 3D view sideways so we get an idea of what's going on. Okay, so I'm going to adjust the azimuth of this ring just simply by grabbing the grip point. There's green circles that are drawn around it, and that indicate the toe spacing that was used for this particular ring. And you notice as I move it, the 3D view changes, the ring view changes, the holes are being adjusted, the charges are being adjusted, the priming positions are being adjusted. All of that's being done automatically. We like to refer to this as our semi-automatic mode, where you're making a manual change, but all of your holes are being adjusted dynamically. In addition to changing the azimuth, we can actually change its burden as well. So I can move it back and forth. Now, we can also, if I right-click on the ring to present the context menu, we can add rings before this or after this. We can invoke a dialog to move rings a specific distance. We can add a slot. We can delete the ring. We can flip individual rings so that their look direction is opposite to what the other rings are. We can re-drill it. We can essentially call up an automated dialog to present the drilling options again and apply them automatically. We can change the hole diameters. We can replace all the explosive types. So if we accidentally put in the wrong explosive type, we can change it. So now with the long section view, I can grab the toe of the ring, and I can adjust its dump or lean. So you can say I can dump it back, or I can dump it forward. So we can take that into account. I can actually move the ring from here and here. Now you might be wondering, these are relatively coarse actions. There's not a lot of precision to them, but we can invoke what we call our stope table to actually change these to be more precise, so that I can make sure everything is back to the way it was. Or you can type in an exact number to get back to where you were. Okay, and it presents the same options as the plan view. With the ring view, we can grab these grip points up here, and I can adjust the sweep angle of the holes. So I can move them all the way down, and then I can adjust the drilling ring, the drill direction. I can move that around, and you see how the parallel holes follow the pattern. So if I move the sweep angles back to give us our full ring again, then you can see how the drill direction affects our ring pattern. And notice as I'm moving the ring, the charges are changing, the holes are changing, the priming positions are changing as well. Okay, so with this, I can also take a look at how the rings in front and behind look. So I will activate that option. So here's my ring in 3D. Let me activate the ring in front, and we'll see how the staggering looks. Sort of a light table effect. Now I can grab this and I can move the ring so that it's staggered with that one, and I can see how it looks with the ring behind it. So it's not too bad. I can move it a little bit more. So you can see how we can adjust our pattern dynamically, all the holes at once, without having to do any extra work. And the nice thing about the way we presented the light table in the 3D view is that it is a 3D view, so I can actually rotate it, and we can see the pattern in 3D. Now those are the semi-automatic modes. We also have an ability to identify where this ring is in the 3D view. So I can click this little button here, and it will show me a plane that represents where my ring is located. So in case your 3D view is not oriented in a way that makes it easy to see, we can figure out where we are. So if we're near the back of the stope or near the front, we can always figure out where we are. And we can do the same thing with the plan view. We can see exactly what elevation we're looking at as we adjust the slider down. And you'll notice in the in the ring view and the long section view, there's a line indicating where our elevation is. Okay. Now if we want to adjust an individual hole, let me pick one. So I want to move this hole down to here. I just pick it and grab that green spot, and we've got a toe spacing circle. So that's why that was moved there. I also want to adjust the collar position. So I can move it so that's a little bit better out. Now if I grab a different hole and move its pivot, I can only move it so far because it detects that the drill mast is interfering with the rotation. So if I move this, notice that the pivot of the mast actually moves as we're rotating it about. So if I were to move this pivot a little bit closer and adjust it, you can see that it actually accommodates the pivot and it moves it back out. So we're getting there. Now other things that we can do besides moving the holes, we can actually select charges. So now I've got my charge selected. I can adjust its collar and you'll see that extra priming points are added. I can move its toe. We can split the charges as well. So we end up with two separate charges. Now within the charges we can actually select our priming points. So I can move the individual priming points wherever we like, so that they're in a better position. Now that I've moved that hole around, I'd like to get it back to where it was, because in this state, once you've made manual changes, that ring is locked. I'm not able to edit it anymore. I can't move it around freely because it doesn't want to overwrite your changes. So to clear those changes out, we can use this redrill option, and I can hit apply and it'll put my changes back to the way they were. Now using this redrill option, I can go through and I can show you some of the other things that we can do. For example, for this ring here, ring 9 through to 12, I want to ignore the contacts so my holes come down. So I'll select them and tell it to ignore the contacts. So I was able to apply those changes to a limited set of my rings. So I end up with a slightly better pattern. Now I also mentioned that some of these holes should extend to breakthrough. So that would be 13 and 14. There we go. So I've got a few extra holes here. Now we're doing pretty good. Let's see what this one is. I think what I'm going to do is just delete that ring. Okay, so we've got a pretty good pattern here. We've seen some of the different options we can do with Aegis. Now I'm going to put a slot in place. So our slot tool is located here, and I already have a pattern loaded, but I will bring it into the editor and explain some features. So our slots are template based, which means that they can be generated once and shared across the site and used as a standard. You can create as many as you like. It's a simple 2D CAD interface where you drop holes in. So you can pick a hole diameter you want to add, and you can just drop them in. And we can select them and clear them out. And if the hole diameter is not available in the drop-down, you just type in what you would like. We can support reamed holes. So I can go from 100 millimeter diameter reams to 200 millimeters, so we can deal with that as well. These holes represent unloaded holes. These holes represent loaded holes, so we can have the different diameters set up. And we're not establishing a timing for this. We're establishing a sequence so that when we use the slot pattern and assign it to a blast, Aegis automatically knows how to time it out based on the sequencing. All right, so I've added the slot to this ring 2. We can see it in our plan view. We can see it in our ring view. Okay, so now I can grab this. I can move it around. So I can change its rotation, so we can aim it any way. It'll go up. It'll work as a blind raise because we can limit its length. We can move these holes around based on our toe spacing. One other thing I wanted to do is I wanted to adjust this ring a little bit because it's a little too close to the end of the box. Alright, so now that we've seen our slot creation, the next step is to take a look at our reports. Before I do that, I'm just going to quickly save it. And our reports are a template-based system as well. They're based on, we based the model on PowerPoint. So we've got our pages over here. You'll notice these are stacked pages. They represent items that'll generate multiple pages. So these ring plots will generate multiple pages. So we've got our typical ring view. We've got all of our items that we can insert into any of these pages based on ring layouts. We have a different set of items for the blasts and the scenarios and the project level reports. So within this view, we have all of these different options to customize the formatting. We can control whether the charges are displayed. We can control whether the reference line is displayed, the color and the line style. We can show the holes. We can control what the meshes look like. For example, for the stope limit mesh, we can set it to use the color that was in the drawing, or we can set it to use a different color. The interesting thing that these options present is it allows you to customize your colors and styles for your site while allowing your users to use the colors that are more comfortable with and still generating reports that follow the standards. So we can show the pivots. We can actually flip the view to be independent of what was generated in the project. So that way, if you have a different look direction for your charging plots as opposed to your drilling plots, you can set that up. We also have a very extensive and customizable table. Let me zoom in on that. So this table has all the formatting options you'd expect. In addition, it also supports quite a large variety of columns. So we can take into account the length. We can control how it's justified and centered, how it's rounded. We can control the position of the units. We can control whether it actually follows the units set in the project, in this case metric, or we can set it to imperial to be independent. And these are the list of items that we have available in this particular table. It's a good mix of drilling parameters plus charging parameters. So if you've got a table that requires some charging data, you can integrate that. You can grab everything from the collar XYZ coordinates to the toe XYZ coordinates. We can also copy this and actually paste it into Excel. And the nice thing about this is it actually pastes in as usable data. So you can actually do calculations with this type of data. So what I'll do is I'll just create a simple bar chart around this. There we go. So bar chart doesn't represent anything in particular. It's just something quick that we could do. And what we can actually do is paste this back into our project. Now this pastes in as a vector file, so you can resize it to your heart's content, and the resolution will be maintained. So the nice thing is that in the reports you can do custom calculations in Excel or another program that's compatible with it, generate some data output, and then you'll be able to paste it back in. So in my second set of pages, I just have a sample of how we could set up a charging plot. Let me zoom out a little bit. And we can see it's very similar to the ring layout, except we're putting more emphasis on the charging. We can also cycle through our report and see how everything fits. So I can look at the rings, make sure I have enough room for the tables. They'll grow for the rings. That's something I haven't seen in a lot of programs, is just the ability to get the formatting right. A lot of times you have to go in and edit it afterwards. So we have a ring summary table where it can summarize all of the costs and drill directions and rings data you can have. And we can have a collar plan view as well. We can set all that up. You might notice the title blocks. I created this in Excel and copied and pasted it back in here. So again, this is a report template. So to apply it, we just simply click on it, and it applies it. It opens up the same editor, but you can see on the left-hand side there are a lot of different pages now that we can take a look at. Now the reason you might want to edit something like this is you may want to put custom labeling in here. So we may want to have some sort of safety notification. I have one stored in my gallery. So we've got a custom arrow that you can customize for each individual ring that may need this particular information. And it's quite easy to add this to a gallery. You just select it and save to gallery, and it'll appear in here. So now that we've got our reports done, the next step is to create a blast. But before I do that, this is our Irides module. So we can just simply select all the rings, select the coordinate system, and then generate the files, and they'll be compliant with the Irides files. So now we create a blast. The way Aegis creates a blast is based on the actual charges within a ring set. So we can deal with ring sets from multiple stopes and combine them. So what I want to do is I want to take the slot ring first. I could pick each charge individually in the order that I want them to fire in. But we have some options available to us to do it automatically. So I can unselect this, and I can click the checkbox, and it goes through, and it automatically figures out, based on these rules, how I want to sequence the holes. So I want to fire the next ring 1 next, and then ring 3. So once you're done with the sequencing, you can take a look at our timing graph, and it shows how the rings will be timed. So we can see the slot fires first, and then the adjacent slot holes, then ring 1, and then ring 2. So based on the sequencing, we can control how the timing is delayed using these various parameters, like between depth primers, between the decks, between the holes and the rings. So I'm going to hit OK on that one. Now, after we've generated a blast, we can actually create an isosurface. What an isosurface is, it's a constant distance mesh from the charges. So in this case, I have it set to 1.5 meters. If I set it to 3 meters, you'll see that it makes a bigger envelope around my blast. Since this blast was set for 3 meters, I'm going to assume it's going to be a 1.5 meter break. So I'm going to set the isosurface up for that. So it shows me what I would be expecting if we assumed the break was going to be 1.5 meters. So this is what it looks like. Okay, so what I'm going to do is rename this blast. I'm going to call it plan. This is what I planned. Normally you'd proceed and you'd add your other blasts in here as well. And actually I think I'll do that. So I'll add the next blast. I'll take 4 rings. Okay. Okay, so I've got 4 blasts. I could go through and isosurface them, and they'll look pretty much the same. But what I have is I have a CMS that represents what this first blast broke to. So I'm going to import that. But before I do that, I'll just I'll make a copy of this plan, and I'll just call it CMS. All right, so I will import my wireframe. Okay, so my CMS is importing. So this is what the CMS looks like as opposed to what the naive break radius approach looked like. So what I need to do is I need to assign this CMS to this blast. So I'm going to assign it, pick it, and it's giving me about 33% dilution by volume. So I'm just going to hide the original. So now this is my CMS. You might wonder what the difference is between my original isosurface and this is. So what we can do, we can create what's called a comparison. So I'm going to compare the planned blast versus the CMS. And I'll name it so it's easy to see. So it's going to go ahead and it's going to create an approximation to the meshes so that we can see what they could potentially look like. So in this particular screen, the important part is that the percent match between the two meshes is only a 48% match. So it's a rather poor approximation. You can see the majority of the mesh is the CMS. Okay, one of the other things I didn't show you is that we can take a look at what the CMS looks like. There's other properties that we can get calculated on it. So we can see the green represents host rock and the red represents ore. So if I hide the ore, you can see that there's a pretty big volume there for waste rock. So it's probably a candidate for the rings to be dropped compared to what we actually wanted. Okay, so we've got a comparison. That was only a 48% match. So what I'm going to do is I'm going to make a clone of this CMS, and I'm going to actually generate a field around it, and it's called a Klein field. It's a linear charge field. So what I'm going to do is I'm going to generate this field. Okay, and we have three fields, as Ian mentioned: a Klein field, a Holmberg-Pearson, and a Lou-Cassabanis. The Klein is a linear charge concentration. So what it represents is how much explosive charge is within a specific volume of a shell. So for this particular case, the white would represent 23.12 kilograms per cubic meter of charge within this small little volume. Now the Holmberg-Pearson is a peak particle velocity field. It will tell you what the peak particle velocity is. So in this particular case, we can move it out, and we actually reach our limits if we go too far with it. So we can bring them in. But I'll stick with the Klein for now, and that looks good, so I'll hit OK. We can actually view that Klein field in 3D and have it rotate about, so we can see it. So we can adjust the contrast on it a little bit to see more detail how that blast is going to look, could potentially look. Now what I'm going to do is I'm going to create a mesh of the Klein field. So I'm going to set it to, I'm going to pick a value. So at 194, this is the mesh. That's nowhere near what we're looking at. Okay, let me change this a little bit here. We're getting somewhere now. Okay, that looks pretty close to what I had before. So I'm going to hit OK, and I'll leave that one there. And what I'll do is I'll create another comparison to see how close that is to the CMS. Okay. Oops, we had a bit of an issue here. Okay, let me restart Aegis. Okay, so I'm going to have to make up some time here, so I'll go a little quickly to get back to where we were. So there's our plan view. Let me clone that. I'll just pull in my CMS really quickly. Okay.
And just one thing to note is that this is Aegis Analyzer, which is still in development, so it's not yet released, and so it might have a few quirks in it still before release.
Yeah, thanks, Ian. Okay, so now what we've got is I'm just going to clear that one out. I'll hide this. So now we're back to where we were. So I'll just make a clone of this. I'll set my client up. Alright, so now what I want to do is I'll generate the field. I had it at about 12, so we can see our fields, and I'll mesh it at, say, 15. Okay. Not sure what's going on there. Okay. Let me generate that field. Then I can mesh it. Okay, I'm not sure what's going on there. Okay, let me just delete that. Sorry, guys. I apologize for that. That's why. I'll just delete this one here. Okay. Now we're back. There we go. Okay. So let me just rename this to Klein. Oops, I spelled it wrong. That's okay for now. And we'll compare the two. I'll save it first this time. Okay, so I'll do the comparison versus this. Oh. Well. Okay, so the last one. There. That's interesting. Okay. That's odd. Okay, I'll just try that one more time. Okay, so what would happen is we would have the blast, and you'd be able to compare it against what the fit was. So let me try cloning that one more time. Okay. Okay. And all right. So, I know what the problem is. Okay. I had it assigned to the wrong mesh. Okay, now I know what it is. There we go. Okay, so we can see what the difference is. Okay, so this is a 53% match. It's a little bit better than what we had. We had about 45. So what we can do now is I'll take a clone of this and we'll do a best fit, and then we can decide what we're going to do. All right, and what we can do is, wrong one. So in this little drop down we have a best fit, and I will do to the CMS. So it'll go through and it'll calculate the best fit for the ISO surface for the Klein field, and this is the shape that it's looking at generating. So if I mesh this, so there's my shape, and if I do another comparison, let's go. So we take the CMS versus this blast. Now we had a 58, now we've got a 78% match. So that's a much better match than we did by hand. So we can take a look and see what the differences are. They're actually pretty good. So now what I can do is I'm just going to make one more clone, and I'm going to generate the rest of my blasts based on that value. So the first step is generate a field, and then mesh it. Okay. Generate a field, then mesh it. Alright, so we're seeing a nice pattern take place. So and it remembers the last meshing value, so I don't have to worry about that. So I'm just going to change the view. Alright, so you can see this is what the blast could potentially look like. Let me do the last blast here. And this is still a work in progress, so I apologize for this oddness. Alright, so you can see potentially what the shapes could look like. Alright, so this is what it can look like, potentially. Now, as the CMSs would come in, you could refine what the values are. You could try the different fields to see if you get better fits. And what I'm going to do is I need to switch to another drawing to be able to show you some of the block model features that we can deal with. But before I do that, I have one report that I want to take a look at. This is a project level report, so we can actually compare the CMSs. I have a table already set up to do that. Oh, okay. Cancel, okay. So I guess it's not going to let us do that. So I'm just going to move along to the other project. And okay, so we have another project here, a simple one. I'm just going to show our ring views. So we've got a little stope in here, a few rings. We've already have the block model imported, so that would be our block model here. So we just need to apply a legend to the block model to be able to see it. So what we can do is overlay the block model over top of our ring, so you can edit your holes based on how the block model looks. We can control how opaque the block model is, so you can just see a ghost of an image and move it from there. We can specify different values, so we can take a look at that. We can supply different legends. They are templates, so they can be shared. And we can take a look at what the block model looks like wireframed. So I can take a look at, just by toggling these legend fields. So I can take a look at what the block model looks like. Now we can actually wireframe the entire thing. And we can see the shape of the block model, how it was set up. We can convert the block model to an actual field. So what we can do is actually set it up so that it looks like a nice little spectral field on each of the rings throughout. So it actually does it quite fast. So you see it's a little bit grainy during the process, but then it's multi-threaded, so as soon as the computation finishes, the nice image is placed in. So we can take a look at what it looks like there. In addition, we can actually look at it. We can visualize it. I can make this a little bigger, so we can rotate it around and see how it looks. We can adjust threshold values. And okay, we can do that, and then we can actually mesh the field. So if I set the maximum value, actually, oops, that's a little too high. Okay, there we go. So I can mesh that, and we can take a look at that and see what that actually looks like. So we could generate grade shells with this, if need be. All right, that is pretty much everything from start to finish. I'm open to questions now.
Okay, thanks very much for that, Troy. We have run a little bit over time, but I'd say we would be able to answer perhaps one or two questions if everyone's happy with that.
Okay, sure. Should I unshare my desktop?
We can keep it on, that's okay. So the first question we've got here, when designing a blast, can rings from adjacent stopes be included?
Yes, they can, because Aegis doesn't really look at the ring structure, it actually looks at the charges. So if the rings in adjacent stopes are in the same scenario, it can definitely be done.
Okay, brilliant. Thanks for that. And one more question. What enhancements to Aegis are planned for the future?
Okay. Some of the first enhancements that are coming up in the next release, we incorporated a new drift repair tool. We encountered a lot of poor wireframes that Aegis just simply couldn't deal with properly, so we developed a tool that can help repair those. We're also importing DXF files in the next release. But on the short-term roadmap, we're looking at doing development, so drifting, potentially shaft sinking as well. We want to also be able to export survey strings for the rings so that they can make use of them in the survey packages, as well as export ring wireframes for tonnage and volume calculations outside of the blast isosurfaces.
Okay, thanks for that, Troy. Now, everyone, we might have to wrap it up there. We have run a little bit over time. So this does mark the end of today's webinar. Thank you all very much for attending. We hope you found the content presented valuable. If you did submit a question that we were unable to address, please rest assured we have these recorded, so we'll touch base with you afterwards to follow up. You'll soon be redirected to an online feedback form. It will take no more than a few minutes to complete, so if you do have the chance, we would really appreciate your feedback on how today's webinar went. We will also be sending out a follow-up email to all of our attendees. This email will provide you with a recording of today's webinar, as well as the necessary details to contact us should you have any additional questions. We look forward to hearing from you soon. Thank you all once again for attending today's webinar, and thank you to our presenters Ian Lepchak and Troy Williams.
Thanks, Eloise. Thanks, everyone, for attending.